Okay, and so there's two ways to define these. So, this one's always omega. It never changes anywhere, right? Because if there's any angular velocity vector, it's the same for every point. But here's how you define the velocity vector, the linear velocity vector, okay, of this specific point. It would be a vector c, which is a location vector that points from that point to any point along the axis of rotation. Okay, the red line. And it can point anywhere. I'm going to prove this to you. But as long as it's pointing to some point along this line, it will work. And you cross product it by the omega, which remember is just the angular velocity vector. It points in the direction. And I said the direction of omega always corresponds with the direction of the rotational axis. Okay, again, it says nothing about its location. C does the job of its location. It's got a cx, cy, cz defined with respect to this that points to some point along there. But this just corresponds with the direction and then, of course, the magnitude of the angular speed that this body is rotating around there. Okay? Okay, and so you'd normally think, okay, well, it's a 6x1 vector. If I want to take the magnitude of it, you just take all 6 components, square them, and add them together and square root it. Well, that's normally what you do. But for twist vectors, that magnitude doesn't have any mathematical significance. Okay? The real magnitude you care about of this whole 6x1 vector is just the magnitude of omega, which is this, which you'd pull out of this. Okay, so let's say we define n as a unit vector that points in the same direction as omega. Okay, except remember, and it's defined with respect to x, y, and z, just like omega is, except its magnitude, if you take all the components of this and square them out and square root them, that equals 1. It's a unit vector, right? The magnitude, the length of it is 1. Okay, which is why when you multiply this magnitude in here by these become omega. Okay, so this is a nice way to think about it. And this is the magnitude. Okay, not the square root of all 6 components here, square rooted and everything. They're added together and square rooted, right? Just pull that magnitude out. That's the magnitude of the twist vector. Okay. Okay, so you're probably still super confused. Let me keep talking about this and hope this clicks with you here. Okay. Suppose omega is pointing out of the page along the x-axis. Okay, so we're going to do like a little example. You probably don't know, like, where did this come from? Like, first of all, why can c point to anywhere on this, and how come c cross omega is v, the linear velocity of this point, if the whole world's rotating around this red axis? Okay, with a speed of omega. Well, let's assume, to help you visualize this c cross omega, let's think of it as this coordinates. Let's take this and move it so that this is the x, that's the y, and that's the z, and say this is coming out at the page at you, rotating in a counterclockwise direction. That's the c vector that points from here to there. Okay, any point along there as it comes out at you. Okay, so you can imagine if the whole world's rotating around this axis in a counterclockwise way, this guy's going to swoop around like that. Okay, and you instinctively know the velocity of this points in that direction, right, at that instant. Well, let's see if that's the case with this. If we take c, okay, and we cross it with omega, okay, then what we get is, remember, omega's coming out at you, so if you move it down here, and it doesn't have a location, right, so you can move it wherever you want as long as it's pointing the same direction, same magnitude. You say c, take your right hand, cross with the omega coming out of the page, and you get a v in that direction. Okay, so you see the right hand rule, you go c through omega coming out at you, and there's your thumb for the velocity. Okay? So you can see it at least points in the right direction it would need to be rotating around that axis. Okay? And you also know mathematically, if you take the radians and times it by this length here, that'll tell you how much it displaces as it rotates. And of course you divide that by time and it's a velocity. Okay, so you can see all the units work out. So hopefully I'm convincing that c cross omega here is v, the velocity of that point. Okay, and of course these omega is the angular velocity of that point and every other point in this world that's rotating around this axis. Okay. Okay, so let's do a specific example. Let's say this is specifically 2 meters away and it's 1 meter up, and say I said its angular velocity speed, or its angular speed, is 2 radians per second, and it's coming out at you going counterclockwise. Okay, well, let's find this. Okay, the omega vector, the first 3 components here, would be, of course, the magnitude here is 2 radians per second coming out in the x direction, then 0, 0, because there's no y and z component. Okay? And then if you define the c vector, it would be, again, it could point anywhere along this axis which is coming out at you. So that this x component could be anything. We just give it some constant value a. You know, like you might be tempted to call it 0, but it doesn't need to be 0. It could be 0, but it's just anything coming out at you. And then, but it's important this be 2 meters, and that's 1 meter. Okay, and remember, make sure you provide your units. Okay, so that's a correct C. In fact, that captures all correct C's. It would work for any A. Okay. Okay, so now let's plug it in here. The first 3 would be this guy, and then you do C cross omega. Now remember, don't do omega cross C. It's important you do cross products. If you don't know them, please brush up on them. The order that you cross product them is critical. Make sure you can cross product C with omega. And when you do that, you find this answer, these last 3 components. So these first 3 components look familiar. They're this. The last 3 components would be C cross omega from here. Okay, and I label them all correctly. They're, you know, the first 3 are in radians per second, the last 3 are in meters per second, because the first 3 are angular and the last 3 are linear velocities. Okay. Okay, one thing you'll notice here is that A just drops out. When you cross product this with that, it doesn't matter what A is, it doesn't even show up in there. So that shows you, that's one crude way to prove that it doesn't matter where your C points to on your axis of rotation, as long as it points to some location on the axis of rotation. Okay, because the final twist vector, which remember, this represents the rotations, and this represents the translations of this point defined with respect to this, as this is rotating around this world here. Okay? Doesn't matter where it points. But let's do a more satisfying proof that it doesn't matter where the C points. Okay? And so let's look at it from a general 3D view. So here's x, y, and z. Here's the C vector. We're pointing anywhere along here. Here's omega. We know that the magnitude of v is the magnitude of C cross omega, which, remember, omega doesn't really have a location. It's just a vector that has a magnitude, a length, and a direction. So you could move it over there to more easily visualize. You do C cross omega, okay? And remember, from cross product math, you take the magnitude of C times the magnitude of omega times the sine, the angle between them, in this case phi. And then you can see that, so it's really this length times this length, which that length is that length, and that's really magnitude of C times sine phi. So it's really the area of this big square is the magnitude, and it's in the direction of the vector that's perpendicular to the plane created by omega and C going into the page, right? You can imagine it rotating around there. It's going down like that, right? So, and that's all fine and good, but, and that's essentially what I said here, except remember, no matter where C points along here, the magnitude of this velocity, well, first of all, of course, the direction's not going to change, because no matter where it points along here, it's still going to define the same plane that the direction is perpendicular to. So the direction's certainly not going to change. But also the magnitude's not going to change, because no matter where C points, the magnitude of C times sine phi is going to be constant. And it's always going to be the shortest distance between that point and the axis of rotation. Okay, it's kind of like the moment arm. The shortest distance between that point and the axis of rotation. And no matter where C is, that's not going to change. And that's what this equation tells you. Okay, so that's a more rigorous way to recognize that it doesn't matter where C points along the axis. It's always going to give the same correct answer. Okay, so now let's look at general twist vectors and screws. So I've only shown you rotational lines. Okay. According to screw theory, or Chassell's theorem, more exactly, all motions can be described as screw lines. Okay? So now, screw lines, I always draw as green lines. That's the line of action there, it's green. And instead of a nice circular arrow around it, I show this squiggly thing, and I'll explain why it's the squiggly thing in a minute. But this has a same thing, a C location vector that points from the global coordinate system to any point along this line of action, this green screw line, and it's got an omega that's the same thing. Its direction corresponds with the, it corresponds with the direction of the axis of, or the line of action, the screw line. So these guys are pointing in the same direction, and its magnitude is the angular velocity, same thing. But now we've got a new thing called a pitch, which I'll explain in a minute. Okay? But first, the twist vector that describes this green line is the exact same, is basically, again, the angular velocity and the linear velocity of this point as it screws around this line of action. Okay, so again, it's a 6x1 vector, and the first three components is angular velocity of all points and the linear velocity of this point as it screws around this line. Okay, you'll see, well, that was the same equation. Well, there is a slight change. You'll notice instead of just omega on top and c cross omega on bottom, it's c cross omega plus p, the pitch, a scalar value, times this angular velocity vector. So there's a little extra, there's two velocity vectors added together to get this linear velocity vector. And I'll explain what it is in a minute. But again, the magnitude of this twist that describes the screw is still just the magnitude of omega. You pull that out, and these are unit vectors n that point in the same direction as omega, but with a magnitude of 1. Okay, so this is the most general form of a twist vector. Okay, I gave you the rotation form of it, which is basically this without this guy. Okay, but now I'm going to add this and explain what it is. Okay, pitch is essentially well, it basically describes, it's a coupled translation over rotation. So think of like an actual screw that you'd screw into a wall. It's got threads around it, and those threads are designed so that the translation of that screw is coupled with its rotation. So as you rotate it some certain number of degrees, it'll always be forced in a coupled way to translate into the wall or out of the wall, right? Depending on what direction you rotate it, okay? So that coupling between the translation per the rotation is the pitch, and it's always a scalar value of a screw. Now in this case, don't think of an actual screw or screw in the wall. Think of a line of action about which we're rotating and along which we're translating. Okay, so the reason I drew this squiggly thing here, let me animate it again, is because this block, if it were allowed to keep screwing around this, it would kind of corkscrew around this like that. It would rotate around it and advance along it. Okay, so so that's what the pitch is, and that's what is multiplied by this omega. Okay, and you can see it's still the units of v, because the units of pitch is meters, and translations per radians, and if you times that by radians per second, you get meters per second, which is linear velocity. Okay, and that's specifically the velocity along this axis that this guy moves forward. Okay, so let's do an example here. If you still don't understand that, you will. Okay, this is very similar to the rotation example, except instead of a red rotation axis coming out at you, I draw a screw line coming out at you, and I color it green. Okay? Okay, so again, its twist vector is defined like this. The top three are the three rotations at this point, and really any point, right? And the bottom three are the three three components of the linear translation velocity of this point defined with respect to that. Okay, and remember, this is not just rotating around it in a clockwise direction, so it's not just doing this kind of thing. It's also, as it rotates, it's coming out at you. So you could imagine if it's really screwing in this direction, it would come here and it would rotate. It would start, rotating around here, coming at the camera here. Okay, so that's what the screw motion is. It's not just rotating around this axis, as you see here, but it's advancing, moving forward as it's rotating. Okay, and hence, by the way, the squiggly thing. It's showing it's kind of rotating but translating forward. Okay, all right, and so let's look at what this component is. It's still the same thing. C cross omega is basically, remember, omega is coming out here. It tells you the direction. It's in the counterclockwise direction, perpendicular to the page, or orthogonal to it, and it's right, and it doesn't have a location, even though we're pointing to the location of the axis. But the omega doesn't have a location. It's just a magnitude and a direction. Okay, and its magnitude will be given in the example. But you can imagine whatever it is, you can move it down here. Take C cross product of that. Take your right hand, And c cross omega, that's the velocity caused strictly by the rotation about this axis. Okay, but then here's the new velocity. It doesn't go this direction, it's going out at you, right? Because omega specifies the direction of this new velocity. Remember, this is just a scalar. It's just a scalar times that will still point in the same direction as that. So that velocity is going to come out like that, okay, which is exactly what we'd expect. P omega comes out like that. So if you add them, you add this vector plus the vector coming out, there's going to be something coming out like that, which is exactly what you'd expect. It would be translating this way and coming out at you, okay, as it screws around the screw line with a certain velocity. But at that instant, this captures the velocity. This twist captures what's going on at every point on this body, no matter whether it's drawn in the center of it or not, right? All you need is, again, the angular and linear velocity of a single point, and then you know the angular and linear velocity of every point of a body that's rotating around a screw axis using this equation. That's the most general one, okay? So let's do an example similar to the last one, except let's put some hard numbers to it. So say it's again 2 meters, 1 meter up. Say it's again the magnitude of the angular speed is 2 radians per second. Now we give it a pitch of 1 meter per radian. Okay, before it didn't have a pitch. Now it's 1 meter per radian. Notice this units in translations per radians. Translation per rotation, meters per radian. Okay, and then that's what it is. Okay, so let's define these things. The omega vector is going to be 2 radians per second in the x direction, 0, 0. Okay, because it's coming out at you at this magnitude, 2 radians per second. Okay, and then what's its c vector? Well, again, you can point to anywhere along this axis. So A, 2 meters, 1 meter. Okay, and then you got to write down its scalar pitch value that has no direction to it. It's just a number. Okay, and now you plug all these into this equation, and you find the first 3 components is just this. Right there. And the last 3 components is this cross product this plus this times that. And if you do that and go do that yourself to convince yourself, you'll get this value. Okay? And notice the A again totally drops out because it doesn't matter where you point to as long as you point somewhere along that axis. Okay? Okay, and so that is the twist described by everything screwing about that axis with these parameters, okay? That captures the angular velocity and linear velocity of that point defined with respect to that global coordinate system, okay? Okay, now, so we've looked at rotations, we've looked at screws. Now let's look at translations, okay? Because translations where we started, and this is actually one of the most confusing, okay? But first I have to teach you some very hand-wavy math. That please don't show any of the math majors what I'm going to teach you, because this is not how you deal with infinity, but it works in engineering. So, okay, so it is a true statement to say that c, this is a scalar value, divided by infinity is 0, right? If you take some finite number of any size, 1,000, 5, -2, whatever you want to plug in there, it's just c, and you divide it by infinity, that's going to be 0. Okay, now, of course, we know there's different kinds of infinity, and we know there's different kinds of 0. Okay, and that's where it gets confusing. There's some sets of infinity, like for instance, there's infinite numbers between 0 and 1, right? But there's a lot more infinite numbers between 0 and 100. Right? They're both infinite, but one set has a much larger set of infinity. So that's how infinity has different flavors of infinity, right? And it's the same thing with 0. Okay, and you'll see this in a minute. It's a lot more confusing to think with 0 because you think 0 just means nothing, right? But it's actually something finite divided by one of these infinities. Okay, and it goes to 0. Okay. So, by this same token, and this is where you can't just flip these, but you kind of can, right? C divided by 0, anytime that happens, in MATLAB or any other program, you get problems. It's undefined. And that's because if you take c and divide it by something that's approaching 0, it starts skyrocketing to infinity. Now when it reaches 0, it is infinity. Okay? Okay, now here's something even crazier that's like, mathematicians would have a cow about, but this is definitely true. 0 times infinity is any real finite number that you want it to be. Okay? Sometimes it's set, and you'll see what sets it, but the point is anytime in engineering you see a 0 times infinity, you can basically get any number you want. And, this is a horrible mathematical proof, but you can see 0 is basically c divided by infinity. Times it by infinity, you can sort of cancel these and you get any c you want, right? This is where math really breaks down. Okay, you can't really do this. This is not how you do math with infinity. But what you should learn is that, this is a way to kind of think about it. But what you should know is 0 times infinity can be any real number, okay? And it depends on the flavor of, what kind of infinity and what kind of 0 it is, okay? How 0 it is and how infinite it is, how large the infinity, okay? Okay, so with that very bizarre little tangent, I'll show you how it's relevant to this, okay? So remember, this is a screw line. Okay, it's got a location vector, an angular velocity vector that's points in the same direction as the axis of the screw. It's got a magnitude that's the angular speed, and it's got a pitch that tells you how much it translates per how much it rotates around there. And it's defined, the top 3 represent the rotations, the bottom 3 represent the translations of this point defined with respect to that. Okay, very good. Okay, and the pitch is how much it translates over how much it rotates. So look at this. Okay, if the pitch equals 0, okay, then that means it doesn't translate. It's like 0 translation divided by some rotation. Means, okay, nothing's translating, everything's rotating, the pitch is 0, and guess what? If nothing translates along this axis and it just rotates around it, then, and the pitch is 0, then this goes away, right? Because if the pitch here is 0, then that goes away. And voila, this now turns red. It's a pure rotation, and this is exactly mathematically equivalent to the rotation. Okay? So really, a rotation is a screw with a 0 pitch. Okay? All right. And so, yeah, so think of it that way. Anytime the pitch is 0, there's 0 translation. There's all rotation. This goes away, and it's just a pure rotation. Okay, very good. Okay, so, but now what happens if that pitch and if the pitch is some finite value, it's a screw, obviously, of the pitch that it's given. But say that pitch equals infinity. Okay, well, what does that mean? That means there was some finite translation, this block, this body, or this coordinate system point is translated along this axis, okay? But its rotation is 0. In other words, it's not rotating. So this is some finite number divided by 0. There's no rotation. And that's some finite number. That's how you get infinity. You take some finite number and you divide it by 0. And this guy goes to infinity. And now, but it gets really weird because if it's pure translation and no rotation, that this angular velocity vector is going to be 0, 0, 0. There is no angular velocity vector because there's no rotation, we said. It's all translation, 0 rotation to get this to push to infinity. Okay? Which means these top 3 are going to be 0. And it also means that c cross this is going to be 0. So it doesn't even matter where c is. It doesn't matter where c points at all. It's going to cross product sign 0, so it goes to 0. Okay? But then this is infinity. Remember, the pitch is infinity times 0, 0, 0. Okay, so we get one of these weird cases in engineering where we have 0 times infinity. In this case, 3 components that are 0 in the omega times infinity of the pitch. And that's how you get some finite velocity values there. So it essentially ends up being these top 3 components are 0 and these bottom 3 components are some v. And they can be anything. Depends on what direction the translation is. They're defined by Vx, Vy, Vz. Sometimes those components are 0, and sometimes those components are something else, right? Some finite thing, but they're produced from times in 0 by infinity. Okay? Okay, so there's a lot of insights into this. This tells you I told you, say a body is purely translating, okay? It's not rotating around any axis, it's not screwing around any axis, it's just purely translating. So remember I told you that if I gave you a single linear velocity 3×1 vector of any point on that body, you would know the velocity of the whole body, because they'd all be the same. Well, that's why you only need to define these three. You don't need these for a pure translation. The other insight that comes from this is that's why pure translations don't have a location. It's the same thing if I said you're going this direction with this magnitude, and then I moved over my location and I pointed the same magnitude in the same direction, no information has changed. There is no location vector for a translation. There's no axis about which anything's rotating. There's no location at all. And that's because it drops away. C is totally irrelevant when this is 0. Okay? So translations are really weird. Okay? But basically, to review, really, and this is what screw theory is all about. This is Chaslow's theorem from screw theory, is that every instantaneous motion is a screw. Okay? And if it's a pitch of 0, if it's a screw with a pitch of 0, it's a rotation. If it's a screw with a pitch of infinity, it's a translation. And if it's anything finite, it's just a screw. Okay? So I'll draw those as red, green, and black. Red rotations, green screws, black arrows are the translations. Okay? And it doesn't need any C vector. This is nonsense. This line of action is just pure direction. It doesn't need a location. As long as it keeps pointing in this direction, you're good. Okay? Okay, so let's do an example here. Again, we keep trying to do this, except here's x, here's y, here's z, here's the c vector, which is irrelevant now because we're saying it translates out of the page at you at 2 meters up and 1 meter over, okay, which is ridiculous because translations don't have a location, but let's go with it, okay? So we say the pitch is infinite, that means it's a translation, and say its magnitude is 2 meters per second. This thing is just flying toward you at 2 meters per second. Okay? It's just coming right out at you, 2 meters per second. Okay? Well, you look at the twist vector for a translation. It's basically just this. Okay, let's write out the omega. The omega, is 0, 0, 0 because it's a pure translation. Okay, the c vector is this, which is going to be very irrelevant, so you're wasting your time. And your pitch is infinite. Okay, and so what you do is you can just take the top three. This is a 3×1 0 vector, which is basically that. Okay, and it's 0, 0, 0. That's the twist. And then the bottom components you get by taking c cross omega, but you're wasting your time because it's just 0. And then you get it plus this omega times infinity, which is infinity times 0, which can be anything you want. But actually, in this case, it's not anything you want. What it can be is any finite real number, but it's forced to be 2 meters per second in this case, 0, 0, because there's no translation in this direction or this direction, just in the x direction given to you there. Okay? Okay, so let's talk about decomposing twist vectors. All right, so okay, so we could now find the twist vectors as a result from any omega, c, and p. So if I give you some coordinate system and I point to some axis with a c vector and I define the direction and magnitude of that axis with an omega and I give it a pitch, you can use that equation and construct a 6×1 twist vector. Well, but the question is, what if I give you a 6×1 twist vector? Can you decompose it and give me the omega, p, and c? Okay, and this is really important because you need to be able to hop back and forth. Okay, right? Sometimes you'll be given the axis of rotation, all this information, and you'll just want to know the twist. You'll want to find the 3 rotations, 3 translations of some specific point. Or you'll be given the 3 rotations, 3 translations, specific point. In other words, the twist, and you'll need to find the axis of rotation and all the other, the pitch and all that stuff. Okay, so to do this, let's work backwards. Remember the definition of a twist. The top 3 are omega, the bottom 3 are v. And here's the definition. That's the definition of v, and that's the definition of omega. So graphically, let's graphically depict this bottom thing, right? So this bottom thing says c cross. So we know c. Here's a global coordinate system. We point c to some. Here's the general twist screw line. Okay, it's green because the pitch is. We're just going to allow it to be anything we want. Okay, And let's graph it. We know omega points there and C points there. So if we take C cross omega, the plane established